All right, so ideal electron configuration. I told you last week that all of those elements that are in that last column there, we refer to those. Does anybody remember what the name was of those? I just kind of said it in passing. It wasn't a name that I gave you. They're called noble gases. All right? And whenever we write the abbreviated electron configuration, what we list first in that abbreviated electron configuration is the noble gas that's on the previous row, right, of whichever element we're writing the electron configuration for. And so the noble gases are those gases that are in the far right column of our periodic table. It corresponds to column 8A, if you're looking at it in the book. And they're called noble gases. Called this because rarely interact with other elements and are all gases at room temperature. Another name you may see for these is inert gases. So they're called noble because they don't react with, like a person, someone that's more noble, you can't easily set them off. They're not going to get in an argument with you easily. All right, they're noble gases because they're noble in that they don't normally react with other elements. And they're gases because they're called noble gases because at room temperature, all of these elements are in that state. They are gases at room temperature. So the noble gases, they all have what we call the ideal electron configuration. All right, and what that means is that they all have their highest energy levels filled with the max number of electrons. Their highest energy levels are all filled with the max number of electrons. All have their highest energy level, thank you. Highest energy level filled with the max number of electrons. Thank you, Jerry. So if you look at the top of page 109 in your book, they have some of the electron configurations written out for 5 of the noble gases. And you'll notice for each of these, for example, Ne has an electron configuration of 1s2, 2s2, 2p6. All right? And so in its highest energy level, which is energy level 2, it has how many electrons total? 8, right? 2 here and 6 here. So a total of 8 electrons. If you look down at the next one that they've got listed out, argon, which is the next element as you go down the periodic table in the next row, 2s2, 2p6, 3s2, 3p6. So again, total of 8 electrons, right? Xenon looks all the same up until here, and where you hit 4. So xenon looks like this. Ditto, right? All of that. And when you get here, you got 4s2, 3d10, 4p6. So even though there's this 3d10 in here, what energy level is the 3d orbital?
3.
It's 3, right? It's the third energy level. So the highest energy level is 4, and in its highest energy level, it again has 8 electrons, right? And so all of these noble gases, they have this this highest energy level filled. What about helium? They don't list helium. But helium is kind of the one exception as far as, so this one has 8 E's as well. This has 8 E's. Helium's the one exception in that it has 2 E's, right? But it's still got its highest energy level filled, because remember the P energy, the P orbital doesn't show up until energy level 2. So the only orbital at energy level 1 is the S orbital, and it's full for helium. So it's got 2 electrons. So that's true of all these noble gases. It has the max number of electrons that it can have at its highest energy level. Yes?
How are you counting? I'm confused on
Are you fine?
how you're getting
8?
8. Yes, because on neon and argon, you're counting the last 2.
Right.
And then on the other one, I just think if I tried to do
So on
that,
this one
I'd be
here?
confused on.
Let me write on this out so that it'll be less confusing.
I would just be confused on how to count the electrons.
Right.
I'd probably put 16 for that one.
For this one here?
Mm-hmm.
And the reason I only counted 8 for that one is because we're counting the electrons that are in the highest energy level. Remember, the energy level is represented by this big number in the front of each of these. So there's the first energy level, here's the second energy level. All of the orbitals that are in the third energy level are this one, and this one's actually part of the third energy level.
Okay,
See
so
that?
all of the highest ones.
That's right. So all of the 4s, which is the highest one for xenon, right? It has a total of 8 electrons. Do you see that now?
Yes.
Okay.
I do. Okay.
So the highest energy level is always full for noble gases. All right? And we refer to that as the ideal electron configuration. The ideal electron configuration is that all of the orbitals in the outer, the highest energy level are all full. All right? We have a special name for these electrons that are out here. The 2 electrons here, the 8 electrons here, the 8 here, and the 8 there. We call those valence electrons. And so let me write that down. Let's see. These electrons in the highest energy level are valence electrons. And so for the noble gases, with the exception of helium, the number of valence electrons will always be 8. But let's take, for example, we'll take one early on in the periodic table. Let's take carbon, for example. Carbon's electron configuration looks like this. 1s2, 2s2, and then we go to 2p. And how many electrons does it have in 2p? 2, right? You start counting over boron, and then you get carbon, so it has 2 here. So in its highest energy level, which is the 2, the 2 is the highest energy level in carbon, it has 2 plus 2, so it has 4 valence electrons. Yes?
Is that an abbreviation for valence electrons, or do we just write out valence electrons?
I usually just write it out. I don't have I don't use anything I typically use as an abbreviation for that. I don't think they do in the book either. So for these valence electrons, it turns out that these are really what determine the chemistry for a particular element. The reason that an element reacts the way that it does is due to these valence electrons out here, valence electrons here. And as it turns out, your periodic table is organized so that the elements, based on the column that they're in, they have the same number of valence electrons. Just like with the exception of helium, the number of valence electrons for everything that's out there in that far right column is 8. Right? They're in the 8A column, and they all have 8 valence electrons. And so those electrons determine the chemistry behind it. So I just want to make sure that you write that down so that you remember that and realize that elements in the same column or group of the periodic table some may refer to those columns as those group of elements. But if they're in the same column, they have similar chemistry. Elements in the same column of the periodic table have similar chemistry. So all the elements that belong to the 5A column or the 5A group of elements, and everybody sees when I say 5A, you see that on your periodic table, right? You see that it's that number and letter that labels that column. All of the elements in the 5A group or the 5A column have similar chemistry because they have the same number of valence electrons. The valence electrons determine the element's chemistry. The ideal electron configuration is when the outermost energy level is full for a given element. When that outermost energy level is full, then that's what we refer to as the ideal electron configuration. Now, is C naturally in ideal? Well, you guys are all still writing that down, so I'll let you finish writing that down for a second. So carbon, just naturally occurring all by itself, is it in that state of having an ideal electron configuration? Is its outermost energy level full? It's not, right? The outermost energy level for carbon only contains 4 electrons. What's the ideal electron configuration? 8, right?
Yeah.
We want 8, so it's lacking 4. It needs 4 more. Huh?
But it can't. Oh, the P. Never mind.
Right? P can hold 6, right? So it needs 4 more to be in its ideal electron configuration. And so as it turns out, this is the reason that chemical reactions happen. These elements, these atoms are trying to obtain this ideal electron configuration. And so we're going to see that. We're going to see it today specifically in ionic compounds. We're going to learn about that more as we talk about covalent compounds. But this is, like I said, that's why it determines their chemistry, because it's trying to get to that ideal electron configuration. And that's why certain elements react with other elements. That's why all of those gases in that far right column don't typically react with anything, because they're already in an ideal electron configuration. They don't need any more electrons to be ideal. They already are. Okay? So any questions about that? Does at least the concept make sense, even though maybe you don't understand how that actually applies to the chemistry? But do you understand what I'm saying with that? Okay. All right. So let's just to kind of represent these valence electrons, the way that they're laid out with an atom, and to understand this idea of trying to get that ideal electron configuration. Let's learn about something called Lewis structures. That'll help us kind of represent what the valence electrons look like for a particular element. So for Lewis structures, you draw a Lewis structure And another name for that is, you might see electron dot diagram. If I asked you to draw the Lewis structure or the electron dot diagram for a noble gas like neon, it would look like this. It would have 8 dots around it, representing the 8 valence electrons that neon has. Right, so that's what neon has, more electrons than that. Right, neon is element 10. So how many electrons in total does neon have?
10.
Has 10, right? 10, the atomic number represents the number of protons and the number of electrons. So it has 10 electrons. But is it 2 ends?
No,
It's just 1, right? Is that right?
Yeah.
Okay. The Lewis structure has 8 dots around it because that represents only the valence electrons, not the total number of electrons, just the valence electrons. All right. In the case of carbon, we said carbon had 4 valence electrons, right? So carbon looks like this. Got 4 dots around it. Because you're only representing the valence electrons whenever you write down the Lewis structure or the electron dot diagram. So even though carbon looks like this, yes?
By valence electrons, do you only need the electrons of the last 2 largest numbers?
That's right.
Okay.
Yep, only the largest. There might not be 2 numbers. Like for example, for let's say sodium, for example, sodium is element 11, and so if you write down its electron configuration, for sodium, it looks like this: 1s2, 2s2, 2p6, 3s1. Right? And so it's only got 1 orbital in its outermost energy level. The highest number there is the 3, right? So it's only got 1 valence electron.
Okay.
And so sodium's electron dot diagram looks like that. Yes?
Is the only way to get their electron dot diagram to write it out like that?
No. So I'm about to show you the trick for doing that, right? So, but I do want you to see that you could get it from this, right? If I didn't tell you what element it was, and I just wrote out this electron dot diagram, you'd be able to you'd be able to count up all these electrons and figure out which element it was for, right? And then you would be able to write down the electron dot diagram. You would add this up and say 2 plus 2 is 4, plus 6 is 10, plus 1 is 11. I look at the periodic table. That's element sodium, Na, has the atomic number of 11, and it only has 1 electron in its outermost energy level. But like I said, they all want to be like neon. They want to have 8, okay? They want to have an ideal electron configuration. I'm just going to write down the first 3 rows of the periodic table just so that you can, not the first 3 rows, all of the elements on row 3 of the periodic table so that you can see what the Lewis structure looks like for each of these guys. And then what's the noble gas on that row? AR. Sorry, I ran out of room at the end. They're getting a little close together. So if you're doing just the electron dot diagram for the single element, just kind of notice, like, take for example S, sulfur. So what you do is you start up at the top, and you do clockwise, and you add the dots that way, right? So So I added a dot here, one dot here, one dot here, one dot here, then I added a second dot there and a second dot there. So that's kind of how you decide where to put the dots if you're doing the element all by itself. But the dots always represent the number of what?
Valence electrons.
That's right. The number of valence electrons for, and I hear some of you guys say valence and some of you say valence. I learned that valence, I think some other teachers say valence. He says it's valence in the book, so you're going to hear me say that, but either way is fine. But I just make sure you understand that it represents the electrons that are in that outermost energy level. All right, the electrons that are responsible for chemically the way this element behaves. Now, what I want you to see now that I've got all these written out, look at Al. How many valence electrons does Al have? Has 3. What column is Al in? It's in 3A, right? You see that at the top of the column? 3A. Look at sulfur on here. How many valence electrons does it have? It has 6 dots around it, right? What column is sulfur in your periodic table? 6A, right? So for all of the columns that end in the letter A, the number in front of that column will also correspond to the number of valence electrons, right? So I could say write down the electron dot diagram for astatine, right, which is AT, which is 85. And because it's in column 7A, I don't have to start counting up electrons or drawing electron configurations or anything like that. I just know it's going to have 7 because it's in column 7A, so I would write it like that with 7 dots around it. Does that make sense to everybody? Because it's in column 7A. Yes?
That's for the valence electrons?
That's right. Yep. So if the column ends in A, the number in front of the letter A will always correspond to the number of dots around the element, which is the number of valence electrons. So the element wants to have an ideal electron configuration, right? So in the case of chlorine, I said, well, let's do astatine since I've already got it on here. It's just like chlorine. How many does astatine have?
7.
Has 7. So it needs how many more in order to be ideal? It needs just one more, right? It's only one away from being ideal. So if it gets another electron, astatine is element 85. So that means astatine normally has 85 protons and 85 electrons. It's electrically balanced, right? The same number of negative particles as positive particles. So the overall net charge of astatine is 0. But if it gets an extra electron so that it's ideal, if it gets 86 electrons and now only has 85 protons, it's got one more negative particle than it has positive particles. So it's going to get a negative charge on it. And so what we call an atom like that is now no longer electrically balanced, but that has a positive or an overall negative charge, we call that an ion. Okay? So an ion is an atom or group of atoms that develop an electrical charge by gaining or losing electrons. So in the case of Cl is just like astatine. Cl has 7 by default. if it gains one more, it gains this new one right here, it's got an extra electron, and so it's going to carry a negative charge. And a negative ion is called an anion. So even though it gained an electron, because the particle that it gained was negatively charged, it has a negative charge on it, an overall -1 charge. That becomes confusing to people sometimes because you have positive ions as well, right? And positive ions are ones that have lost electrons. Like, well, why is it positive if it lost? Well, because it lost a negative particle and became more positive. All right? So a negative ion is called an anion, and with negative ions, you change the name of the element to end in IDE. So Cl minus, that's how you would write it if you were just to write it out in a chemical equation. Cl minus is a chloride ion. Not a chlorine ion, a chloride ion. That's only for anions. It's only for ions that have a negative charge. We change that suffix at the end to be IDE. Now, of course, you can have positive ions as well. And so let's look at, for example, sulfur. Sulfur is in column number... Oh, wait a minute. No, I don't want to look at sulfur. I want to look at sodium. I don't know why I said sulfur. Sodium. If I look at sodium, sodium is in column what?
1.
Sodium's in column 1, right? So it has a single valence electron. Well, for chlorine has 7, so it made way more sense for it to gain 1 electron to become ideal, right? But sodium, if it went the route of gaining electrons, it'd have to gain 7. It could do the opposite. It could lose electrons. And so if it loses 1 electron, now it's actually ideal, right? Because before, sodium had had 11 protons and 11 electrons. If it lost 1, now it has 10 electrons. And if we were to write out the electron configuration for sodium, it would look like this. That's what it looked like before, right? Before it lost this electron. But when it loses the electron that's out here. And so now look. Its outermost energy level is full. Now that it has only 10 electrons. Okay? So for the elements that are on the left-hand side of the periodic table, they're going to want to give up electrons to become ideal. Whereas the elements that are on the right side of the table, they're going to want to gain electrons to become ideal. All right? And so since it lost an electron, it lost a negatively charged particle, now it's got more positively charged particles than it has negatively charged particles, and so it's going to have a +1 electrical charge. It lost an electron to become ideal. So is a positive ion or a cation. That's what we call cations. So we have anions and cations. And with positive ions, we don't replace the suffix at the end with "-ide". We keep the same name. So this is a sodium ion. That would be the correct name for it. So if it's a positive ion, you just keep the name of the element and call it that. If it's a negative ion, you add that "-ide" suffix to the end, like with chlorine. Questions? Anything confusing at this point? All right, so which elements want to get rid of electrons and become cations? The elements on which side of the periodic table? On the left side of the periodic table. So what color are the boxes, except for the H at the top there? What color are the boxes over there? They're all purple. They had to tell me that in first class. I couldn't tell what color it was. But what does the purple color correspond to as far as the categories at the top?
Standard metals.
They're standard metals, right? So metals typically lose electrons and become cations. Non-metals, which are the ones on the right side of the page, all the blue ones there, right? Non-metals typically gain electrons and become negative ions, all right? So let's kind of write down these distinctions between metals versus non-metals. So the first thing that we said was they tend to lose electrons. I'm going to abbreviate that as capital E apostrophe S. Lose electrons to become ideal. Nonmetals, on the other hand, lose electrons to become ideal. You're right. I just did the reverse of that. Thank you. I do those just so you guys have an opportunity to get some extra credit, right? I knew I did that, of course. All right, what's any other differences that you just kind of know about from observing metals versus non-metals that you can tell me characteristic-wise? Metals, what do you usually think of when you think of a metal? How can you identify? How do you know? How do you look at this chair right here and go, well, this isn't metal, but this probably is? Shiny, right? Metals are generally shiny. They shine. They're shiny or have luster, right? Have luster. Maybe another way to write that. Non-metals are not. They're typically not shiny. Something else. Metals, they're typically malleable. And by the way, I want you to make sure you know these characteristics. They're malleable. What do I mean by malleable? Anybody know? Yeah, they can be bent, shaped, right? Very good. So bendable, you could rewrite that as bendable. You know, without breaking, you can shape them. On the other hand, nonmetals are usually brittle, and they break easily. And finally, something else that you probably already know about metals is they tend to conduct electricity and heat. They conduct electricity and heat well, whereas nonmetals do not conduct electricity and heat. All right, so those are just some of the properties, some of the characteristics to distinguish between metals and nonmetals. But now you know from a chemistry point of view, metals also tend to lose electrons to become ideal, whereas nonmetals tend to gain them. All right? So make sure you know those differences just in case, hint, hint, it shows up on a test, right? All right, so let's talk about ionic compounds. Use these Lewis structures a little bit more. Nope. Ionic compounds. Okay, so consider table salt. Who can tell me what two elements table salt is comprised of? Does anybody know? Give me one element. So yeah, sodium chloride. So I saw Isabella put her finger up first. She was tentative. She didn't want to raise her whole hand. It's like, maybe a finger, maybe I know. Isabella, you are correct. NaCl. Right? That's the chemical compound that we refer to as table salt. It's also called sodium chloride. Do you notice anything about the naming convention of that? Chloride, right? We just talked about that. So it ends in IDE. And that's because this compound is comprised of ions. Sodium and chloride ions. All right? Let's see how that works. So what's the Lewis structure for sodium? It has one electron, right? It's in column 1A. So we can just look at our periodic table, see that it's in column 1A. It's got a number 1 in front of it, so we know it has one valence electron. What about chlorine? 7. It's in column 7A. So we put 7 dots around chlorine. So sodium is what kind of element? Metal or non-metal? It's a metal. So on the left-hand side of the chart, remember the color on the chart and the position on the chart will help you identify that. Yes, sodium's not one that we typically think of, right? It's something shiny, but it is technically a metal. Chlorine, on the other hand, is on the far right side of the chart. It's blue, a blue-colored box, so it's a non-metal. Metals want to give up electrons, and that's great news for the non-metals because non-metals want to get electrons, right? And so this sodium wants to give up one electron to become ideal, and the chlorine atom wants to gain one electron to become ideal. So what happens is this sodium gives its electron to this chlorine atom, and now they're both ideal, right? You see that? So if this element here has no dots around it or 8 dots around it, it's considered to be ideal. So this, I guess I could have, to make this a little, I'm not going to. I could have gotten out like the red marker and could have shown that this dot wasn't originally with the Cl, that it came from over here. But I don't want to do that. It takes too much work. So you guys can imagine that in your head, right? Use your imagination, right? So you guys see that? It had one extra. It donated it to chlorine. So this wanted to lose an electron. This one wanted to gain. Wanted to lose one electron. And this one wanted to gain one electron. So it's perfect. And so together, when it lost an electron, then this Na became positively charged, right? And the Cl, whose Lewis structure now looks like this, became negatively charged. And so because opposite charges repel or attract? They attract. Right? And so since opposite charges attract, it's that attraction between those opposite charges that actually hold this compound together. That's why this chemical reaction happens and they bind together. All right? And an NaCl is an example of what we call an ionic compound. Because when this compound forms, it forms because we created two ions that are now held together, right, by their opposite charges. So ionic compounds the definition for that. An ionic compound is a compound formed by cations, positive or negative ions. What's a cation? That's the positive. Cations and anions, that's the negative one. Held together by their mutual attraction. And so now, based on what we learned about metals and nonmetals, these ionic compounds are usually formed. They're compounds that are usually formed between metals and nonmetals. I'll give you a burrito while you guys finish writing. Is that clear to everybody? All right, let's take another example. Let's say instead of chlorine, let's pick another nonmetal. This time, we're going to do sulfur. So sulfur is in column what? 6A. So it has 6 valence electrons. So it looks like this. I'm going to write my dot down here. You'll see why in a second. So this wants to lose 1 electron. This guy here wants to gain how many? 2, right? It's got 6. It needs 8 to be ideal. So it wants to gain 2. Let's put his electron back. Well, now we have a problem, right? Because sodium only has 1 to give up. Sulfur needs 2 to be ideal. I did it this time. I can tell you guys weren't in an imagining mood, right? So here we go. There. Huh? Is that pretty exciting for you guys? Yeah. Okay. I see some smiling faces. That's awesome. That's what I live for, those moments, right? To look out and see the class smiling. So sodium wants to lose 1, but this guy needs 2. So what do? Well, we just bring another sodium atom into the equation, right? Now, this guy needs 2. We've got 2 sodium atoms that are wanting to give up 1 for a total of 2. So this guy donates his 1 here. And this guy donates his 1 here. So now, everybody's happy, right? Everybody's ideal. So you've got something that looks like this. You've got a sodium ion with a positive 1 charge that donated, you've got 2 of those guys actually, that donated a total of 2 electrons to this sulfur atom. And because it has 2 electrons, it doesn't just have a negative 1 charge, it has a 2 negative charge. All right? So when we write the charges on these ions, if it's not a 1, the 1's always understood, and so we just leave it off. But if we have to write the number, you put the number in front of the charge instead of after the charge. All right. So it has a 2 negative charge, and the chemical formula for this is that you have 2 sodium atoms for every 1 sulfur atom. And so what do we call this compound? What's our naming convention? What would we name it?
Sodium sulfide.
Sodium sulfide, that's exactly right. So for the metal, we always keep the full name, right? But for the non-metal, we replace the end of it with "ide." So sulfide, very good. All right? I'll give you another point if they weren't already up there, Chris. Questions about that? Is that clear on everybody? Or to everybody? Yes.
What about if we use something like magnesium rather than sodium?
So magnesium, and instead of sodium, so let's do that. That's actually kind of our next example here. I totally paid Cruz to ask that question, so that you give me a good segue into the next section. What do we do with something like sodium or like magnesium? He said. So let's see how that would work. So with magnesium needs, it's in which column?
Second.
It's the second column. So it's got 2, right? And if we stick with sulfur again has 6, right? So in this case here, magnesium wants to get rid of 2, sulfur wants to gain 2, so it's actually a perfect match, right? We're in good shape. So this guy could just donate here, this guy could donate here, and just to make you guys happy, because I like to see those smiles. Look at there, right? So we've got 2 little red dots over here for the sulfur, and our dots go away for magnesium. And so in this case here, Mg, since it lost 2 electrons, what would the charge be on this ion? It lost 2 negative particles, so it became more positive. Huh? It would be 2 positive, right? But the sulfur, on the other hand, gained 2 negative particles, and so it has a charge of 2 negative. But what actually combined? It wasn't 2 Mg's and 2 S's, it was just Mg and S, right? And so when you write these charges down here, if the numbers are the same, you just remove the numbers altogether. All right? Because you don't need multiple of them to combine. They're already matched up perfectly to combine. Does that make sense? This one wanted to get rid of 2. This one wanted to gain 2. So we didn't need any additional, didn't need to invite any extra atoms to this party. Right? They were good to go. Now let's do one that's a little more complicated, and I'm going to give you a couple of rules to do, for example, magnesium and phosphorus. Okay? So shortcut for combining ions. First of all, the first step is you want to determine, make sure you know these steps here, determine what charge would exist if element becomes an ion. So in this case, we're doing magnesium and we're doing phosphorus. Okay? So magnesium is in column what? We just said that was column 2. I'll let you guys finish. I'm sorry. You're writing down. This is not IO, this is ion. Comes an ion. So we're trying to see how magnesium and phosphorus would combine. And the first step, the shortcut way of doing that, so we don't have to write out these Lewis structures and kind of figure out how the electrons would piece together, right? Is we first see what the charge would be if these elements became ions. And so Mg is in column 2A, right? So it has 2 valence electrons that it wants to get rid of. And so if it were to get rid of those valence electrons, it would have a charge of 2+, right? Is that clear to everybody? These are like simple things that if it doesn't quite click the first time, the rest of it's not going to make any sense, all right? So if you don't know why I put 2+ in there, please stop me now and let me go through it one more time. Anybody want to raise their hand and say, I didn't quite follow that? You can just wink at me so no one will see that you raised your hand, right? And I'll totally call you out for the whole time. No, I won't. All right, what about phosphorus? What column is it in? Huh? 5. It's column 5A, so it's got 5 electrons, right? It's got a Lewis structure that, I did that wrong, looks like that. And so it needs how many more electrons to be ideal? It's got 5, it needs 3 more, right? So if it got 3 more electrons, it'd have a 3 negative charge. So that's what it would look like if I just wrote it as an ion, wrote that element down as an ion, right? So that's our first step. Determine what charge would exist if element becomes an ion. The next step, drop the charges. Drop the charges. Switch the numbers. And make subscripts. So the numbers, make the numbers subscripts instead of superscripts. Superscripts are when the numbers are up here. Subscripts are when the numbers are down here. Right? So that's going to be our step, and I'm going to the way that I'm going to write this down so maybe it'll stick with you. What you're supposed to do is swap and drop. All right? We're going to remove the charges. We're going to drop the charges. We're going to swap the numbers and then drop them down. All right? So for this guy here, what that means that we do is we remove the charges, which would be like this. So it would look like this here. Right? We're going to swap them. So we're going to put the 3 over here. We're going to put the 2 over here, and then we drop them down. So then we're going to put the 3 here, and we're going to put the 2 here. So you see how I just swapped those around and dropped them down? This is the chemical formula for that compound. That's the chemical formula for what compound? What would that compound be called?
Magnesium phosphide.
Magnesium phosphide. Excellent. Very good. Don't tell me your name. I know your name. Lily. Sorry, just my brain cramps up sometimes. All right, so magnesium phosphide is what this would be called. The metal always maintains its normal name. The non-metal gets an "ide" on the end. All right? Now, the one other step that you may want to write down is if numbers are the same, remove them. So we saw that one case, right, where the charge on them was 2 plus on one and 2 negative on the other, and you just remove the charges altogether. if that's the case. What was that? That was maybe magnesium sulfide. All right. Any questions about that? We're going to do an example and try it out a couple more times. But yes.
Whenever you swap and drop, how did it lose its negative charge?
It didn't really lose its charge. This is just a shortcut way to figure out what the chemical formula is.
So
Okay?
it's still negative?
The ion still has the same charge. Well,
Oh yeah, and
the reality is what happened is instead of having let me write down the Lewis structure. You have something to say?
because if we just saw that, like the Mg3P2, how would we know that the P has a negative charge to call it magnesium phosphide? Like, I
We
think
know
that's
that it's phosphide because that's the nonmetal. Our rule with ionic compounds is the metals always keep their name, and the metals are always written first. The nonmetal is always written second, and if it's an ionic compound, it's going to have "ide" on the end.
But how would we know?
How do you know which is
Didn't
which?
see the charges.
Well, you know where they are on the periodic table, right? We determined those charges. I didn't tell you those. You looked it up on the periodic table and figured that out yourself, right?
Okay.
So if I just say magnesium and phosphorus, you look at the chart and you go, oh, magnesium is a metal. And so it's going to have a 2+ charge if it were an ion, right? If it was an ion. Phosphorus is a nonmetal, so it's going to have a 3- charge if it's an ion, because it gained 3 electrons. All right? So we looked at the periodic table to figure that out. And so we know what the proper order should be because we know by looking at the periodic table that Mg is the metal and phosphorus is the nonmetal. Metal always comes first, nonmetal always comes second, nonmetal always ends in IDE. Does that make sense? And then as far as the charges, again, you know that because of which column it's in the periodic table. You know Mg is going to have a 2+ charge because it's in column 2A, and so it has 2 valence electrons and it wants to get rid of those. You know that P is going to have a 3- charge, but it's because it's in column 5A, so it's got 5 valence electrons and needs to get 3 more to be ideal, and so it has a 3- charge. But this right here, the whole swap and drop thing, is just a quick way for you to go from here to what the actual chemical formula would be. Okay? The alternative way to do that is you could draw their Lewis structures, right? You could say, okay, Mg looks like it's in column 2, so it has 2 valence electrons. And here's what I'm going to do. I'm going to put those valence electrons over here. All right? P has how many valence electrons? 5, right? Okay. So I'm going to draw P like this, but this one needs 3, and this one's only got 2 to donate, right? And so we're going to put another Mg down here because we got to get some more valence electrons from somewhere. But if this guy let me get my red marker. So if this guy, let me do my Mg's like this. So here's my Mg's, right? This guy needs 3, so he could donate to here, right? Give him 2, and he could donate 1 and give him 1. Now this guy's ideal, right? But we got a problem, right? Because he donated this, and he donated both of these, but this guy's still got this one extra one hanging out here that it wants to get rid of. So what are we going to do? We're going to use another phosphorus atom, right? The phosphorus atoms have 5 valence electrons. And so now he can donate to right here and give him that. So he's good, right? But this guy still needs 2 more. So what are we going to do? We're going to take 1 more magnesium atom over here, like this. Magnesium has 2. So he's going to donate both of his 2 right here. So now the phosphorus one is ideal, and the magnesium is ideal. Everybody's happy. Everybody's got the right number of electrons. How many? We have 3. How many Mg's do we have in our chemical formula here? 3. How many phosphoruses? just like what we have here, right? So you tell me, would you guys rather figure out this chemical formula by doing this? Or would you guys rather just figure out what the ions would be and swap and drop, right? It's just the shortcut way to get to that, to tell you how many of those that you need in order for the electrons, the valence electrons, to all work out. Okay? Does that make sense? That's the purpose of learning the swap and drop thing. Okay. Let's see. So let's do some examples on page 116, example 4.4. What is the chemical formula of the and name of the ionic compound formed between magnesium and fluorine? All right, magnesium and fluorine. I'm going to do it up over here so we can all see it. Magnesium is in column what? 2A, right? It's a metal, so it's going to be a positively charged ion because it wants to get rid of 2 electrons. So it has a 2 plus charge as an ion. What about fluorine? What column? 7A. Yep. It's in the second row, 7A. So it's got 7 electrons. It wants to get 1 more. So it's going to have a 1 negative charge. Notice we always leave the 1 off. We never write the 1 down. 1s are always understood. And so our rule is to figure out the chemical formula for this is to swap our numbers, drop those charge signs, swap the numbers, and then drop the numbers down to make them subscripts. So if we do that, if we swap and drop, we got MgF2, right? 2 comes over here to the F and drops down. 1s are always understood. We don't write those down. Is that clear to everybody? How we did that? All right, let's do another one. What's the name of this? I heard something like magnesium. What? Somebody be assertive. What is it? Magnesium fluoride. Thank you. All right. But I wrote it fluoride. It's Fluoride. Right. Magnesium fluoride. Very good. Give the name of the chemical formula of the ionic compound that's formed between aluminum and sulfur. Al and S. Al is in column 3A. So it has what charge on it if it was an ion? Huh?
Positive.
Yep, positive 3 plus. Sulfur is in column what? 6A. So it needs 2 more electrons to be ideal, so it's going to have a 2 negative charge. We swap and drop, and that becomes Al2, S3. Swap those numbers around, drop them down. And our name? Aluminum sulfide. Very good. That was much more assertive. I like that. Aluminum sulfide. And then finally, calcium and selenium. Calcium, selenium, Se. Calcium is in column 2A, so it's going to have a 2 plus charge. Selenium is in column 6A, so it's going to have a 2 minus charge. It needs 2 electrons. So when we swap those guys, it becomes Ca2 and Se2, but like I said, if the numbers are the same, remove them. So we just remove the numbers when they're the same. So it's just CaSe, and it's calcium. So it's kind of a weird one. Selenide. Right? All right, last thing. Any questions before I move on? We got that? Everybody thankful for the shortcut? And I wouldn't want to have to write out those little structures every time, right? What about compounds that don't follow, or elements, metals that don't follow these rules? What are some ionic compounds that don't follow these rules? Gold. Gold? basically the stuff that's in the transition metal regions. Those don't tend to follow the rules. All right. When you're working with those transition metals, you'll notice that they're in columns 1B to 3B, and 1B to 8B. It's weird because it starts with 3B. 1B is actually over there near the end. But 1B to 8B, those are all transition metals. And so you're not going to know the charge unless I give it to you, or I tell you that it's being combined with a particular element, and then you can figure out the charge that way. So what's an example of that? So copper, for example, can combine with chlorine in two different ways. It can be one copper atom for each copper chlorine, so for each chlorine atom, or one copper atom for every two chlorine atoms, right? Both of those are valid. And so for this first one here, here's the thing that you have to remember, that when these compounds form, overall they're electrically neutral. All right, the charges balance out. And so even though we don't know, since Cu is a transition metal, even though we don't know what the charge is on the Cu, we can figure out what the charge is on the Cl. Because Cl is in which column in our periodic table?
7A.
It's in column 7A. So if Cl is just an ion all by itself, it's going to be Cl negative, right? And so what that means is for this one here, Cu, if Cl is negative, if it just has a -1 charge because there's only one chlorine atom, then the overall charge for the atom's got to be 0. If the total charge has to be 0, then what does the charge on the Cu have to be? +1, right? Just a +1. So we write, it would be like that. And so the way that we would write this out is we would say copper, and we would use a Roman numeral 1 to signify that it has a +1 charge. Okay? Copper 1 chloride is how we would write that. Okay, so if it's a transition metal, you use the Roman numeral to signify what the charge is on the metal, or what the charge of the ion is. All right? Now, in the case of CuCl2, in this case, because Cl all by itself carries a -1 charge, but we have two chlorine atoms, then the overall charge is going to be 2 negative, right? For the chlorine atoms, for the chloride ions, 2 negative. So, in other words, so the point is, in order to balance this thing out so that the total charge is 0, in this case here, copper is going to have a 2+ charge on it. And so we would write this one as copper 2 chloride. So does everybody see how we figured that out? Because we know the charge on the non-metal, it makes it possible for us to figure out what the charge has to be on the metal and on the transition metal. So the Roman numeral, right? Make sure you recognize that the Roman numeral tells us the charge. So let's say, for example, we, you know what, let's do an example, because the example I think will give us the opportunity to do it both ways. So example 4.5 on page 118. So here, they don't do like we did it here, where they give us this first. In the first question, they tell us what the name of the compound is, and they say, give me the chemical formula for this compound. All right? So they say, what's the chemical formula for the compound cobalt-3 oxide? Cobalt-3 oxide. So it's a compound formed from cobalt and oxygen, right? Cobalt and oxygen. Cobalt, if you don't know where it is on the periodic table, you can look at your list of elements on the right side of the front of your book. Look for cobalt. Cobalt is number 27. It has an atomic number of 27, and the symbol the atomic symbol is CO, right? So CO is cobalt. What is the charge? It's a transition metal. You can see it like right in the middle of the periodic table there. What's the charge of cobalt in this compound? 3 what? 3 positive, right? 3 plus. Because it's a metal, it's going to have a positive charge. It's going to be a cation instead of an anion, right? So 3 plus. Oxygen, we can figure that out from the periodic table. It's in column 6, right? 6A. It's in column 6A, so it needs 2 more electrons, so it's going to have this charge as an ion. And now we're back to what we've already done multiple times, right? We're swapping and dropping to figure out what the chemical formula is. So we swap the numbers and drop them down. The 2 goes here, the 3 goes there. That's our chemical formula. Okay? Now let's do it in the other direction. Any question about that? Everybody clear on that? All right. Iron can have more than one charge in ionic compounds. What is the name of FeCl2? So they ask us to give them the name of FeCl2, and they note that iron can carry more than one charge because it's a transition metal. All right. So this is the example that we did just a moment ago. We don't know what the charge is on Fe yet, but we do know that for Cl is in column 7A, so it has a charge of -1 as an ion. And since we've got 2 chlorine atoms, then the overall charge for Cl2 is going to be 2 negative. Right? Everybody clear on that? You basically take whatever number is here, and you multiply it by the charge of a single one of those atoms, right? So if this happened to be oxygen, which has a 2 negative charge, but we had 2 oxygens, then the overall charge would be 4 negative here. Does everybody see that? Right? So this number multiplied by the charge of a single ion. So 2 negative is the charge of the Cl. So in order for the overall compound to have a net charge of 0, then the Fe has got to have a charge of 2 plus. That way the charges cancel one another out, and it's electrically neutral. And so if this is 2 plus, then our name for this compound is iron Roman numeral 2. Right? Chloride. Is that clear to everybody? All right. So I want to wrap up this section with doing a quick experiment. I still got a few more notes, so don't put your notes away yet, right? I'm just going to do this at the front of the class so you guys see it. But what I have here is a plastic container and this is an experiment that shows you an example of electrolysis. All right. What is electrolysis? Electrolysis is the definition for you. Electrolysis is breaking down a chemical using electricity. All right? And so what we're going to do is we've got these thumbtacks in the bottom of the container here, these metal thumbtacks. So we're going to apply a battery to the bottom of this. So if I stick my battery to the bottom of these 2 thumbtacks here that aren't touching one another, is it conducting electricity yet? No, because the circuit's broken, right? You'd have to have a wire that connected those 2 together. So, but if we put a solution in here, if we put a compound in here that conducts electricity, right? Or if we had a metal, like with a metal wire, something that would conduct electricity, then that circuit would be completed and the electricity would flow, right? And so we're going to see if we can do that with a couple of different compounds here. So what we're going to start with is we're just going to add some distilled water to this. All right? So we've always heard that, you know, if it's a thunderstorm, get away from water. Why? Water conducts electricity, right? So I'm putting water in here. I would kind of expect then if I stick this battery to the bottom that something might happen. That it might start conducting electricity and I might see something. And what will happen is if it does conduct electricity, electrolysis is going to start happening. What's going to happen is it's going to break down this chemical. The chemical that's in here is water, and so the H2O is going to start breaking down if we can conduct electricity. But as it turns out, do you see anything happening there? It's pretty uneventful, right? Looks the same. Nothing exciting happening. Everybody see that? Y'all want to share in the non-excitement? Huh? Yes. Unthrilling, correct? Yes. All right. So that nothing exciting happened there. Let's try mixing something in here with this. We're going to put some sugar in here first and see if we can cause this thing to conduct electricity. Cause this solution to conduct. The reason it did not conduct electricity, even though we've always been told that about water, is that pure water actually doesn't conduct electricity. The reason that rainwater and salt water and water in the lakes and all conduct electricity is because they contain something called electrolytes in the water. Okay? And I'll write down the definition of an electrolyte. Electrolytes, these are chemicals that form a conductive solution when dissolved. All right? Chemicals that can form a conductive solution when dissolved. Now, as it turns out, that because ionic compounds split up into ions when dissolved. What are ions? They're atoms or groups of atoms that carry an electrical charge, right? The Na, when it became Na+, now it's not just a sodium atom, it's a sodium ion. So it's an atom with an electrical charge. So because ionic compounds split up into ions when they're dissolved, the solution will conduct electricity. All right? So we know that if we put we've established the fact that this distilled water, the water that's got any impurity removed from it, we've already established that it will not conduct. We just added sugar to this water. And so, if sugar is an ionic compound, then what should happen once I apply the battery to it? It should start breaking down. You should see electrolysis, right? The breakdown of water, and when water breaks down, it breaks down into hydrogen and oxygen gas. So we should start seeing some bubbles, basically, right? What do you think is going to happen? Here's where we hypothesize, right? What do you think is going to happen when I apply the battery? Are we going to see bubbles or not? Elizabeth says no. Anybody want to challenge her and say, you're wrong? You're going down. Nobody? Why not? Cruz says you're going down. You're dead meat. All right, let's see. Wow. Do you guys see that? I am totally underwhelmed again, right? No bubbles. That is very unexciting. Cruz, Elizabeth just ate you for lunch, man. Took you out. Nothing. No bubbles. So, the reason there aren't any bubbles is because sugar is not an ionic compound. sugar is what we call a covalent compound, which we haven't learned about yet, but we will in later chapters. Covalent compounds are not held together by electrical charges the way that ionic compounds are. Covalent compounds they don't give the electrons away and become positively or negatively charged. Covalent compounds actually share the electrons. So we'll learn about that later, but let me rinse this out first. I'm going to rinse it out with the distilled water, because if I use the water from the tap, why is that not a good idea?
Because it's not distilled.
It's not pure, right? So I'm introducing electrolytes just by taking it from the tap, and so our experiment, our container's contaminated, and it wouldn't be a good test. It might start conducting electricity, not because the salt is ionic, but simply because I used impure water.
Salt's ionic.
But we know salt is ionic because we've already used salt, right? In as we were doing our some of our Lewis structures. So I'm going to add some more water, and this time I'm going to put some salt in there. Put about a teaspoon of salt. I'm just going to put all the salt in there. I mean, this bag, there's hardly any in it. I'll leave a little bit so that the next teacher, they're like, what? That's all the salt that he left me? Stick it back in the cabinet. I'll replace it. All right, so we're just going to mix this in. The salt took a while to dissolve, so it stays cloudy for a bit. So while we're sitting here waiting for it to dissolve, what's on your mind, Artie, now? Anything you want to share with us? Any big news?
My family recently adopted a dog.
Oh, really? Okay, cool. What kind of dog?
Lab collie mix.
All right, nice. How old? Do you know?
About 1 or 2.
About 1 or 2, so still like puppy-ish?
Yeah, very puppy-ish.
Wow.
Very excited about everything.
I was going to say, I feel very sorry for you. We've always had like dogs from puppyhood. And, you deal with all the barking and the chewing and the, just very hyper about everything. So we adopted one that's like 3 or 4 years old. She's a lab mix. We don't know what all she is exactly. But so laid back. So much easier than the puppies. It's like, we will never get a puppy again. They're cute for like 3 days, and then they grow up. And it's like, you're not cute anymore. Leave me alone. All right. Cool. I'm glad I asked you about that. Nice. Anybody else have something they want to share while we dissolve here? Then you can't top the puppy story, huh? It's like, well,
she's a chill dog. She was at the park. And
oh, really? That's good. That's good. Our last dog was a beagle. My wife, it was actually the first dog that wasn't just given to us, that we picked on our own. And my wife did all this research trying to figure out what was good with kids and all, and it was like Beagle. Beagle kept coming up. I can't figure out how in all of her research that she never read anywhere that they bark incessantly, non-stop, right? I mean, it's like the dog would start barking at a leaf. That leaf fluttered there. And so the dog starts barking and you're thinking, he'll quit after 30 minutes, like 3 hours later. It's like, how do you still have a voice, and it's that loud howl, So, yeah, we won't be getting beagles anymore. All right, so let's see what happens. What's your hypothesis? Since we know that salt is an ionic compound, then what's going to happen? When you dissolve ionic compounds, they split up into their ions, and so you've got these charged particles floating around in there, and because you have charged particles, the solution should conduct electricity. So we should see something much more exciting whenever I stick the, I'm going to stick it to that side. Can you see anything?
I see some bubbles.
You can kind of see it from the top. You see it? Mm-hmm. All right, so bubbles are definitely being produced. Let me see if the camera can get that.
That's too high.
Too high? Oh, is that it? Okay, thank you. That was close. Glad you were here. I mean, do you know how much flack I'd have called about that? As students were looking at it later, I couldn't see it, Mr. Walker. I had to redo the whole class. Y'all would all have to come back and we'd sit through it again. So close. All right, do you see it? You see it? But it is breaking down the water and it's producing a gas, and that's what the bubbles are there. All right? Okay, so Does everybody have the data that they need for their lab report? We did just a pure distilled water solution, did not conduct electricity. We did a solution with sugar, about a teaspoon of sugar added to it, did not conduct electricity, so we surmised from that that sugar is not an ionic compound. But then we did salt, which we'd already gone over in class was an ionic compound, and sure enough, when we did the salt, we began to see electrolysis. The water was breaking down and it was forming a gas in the water, right? So that should be an easy 100, right? Experimental error. Where might we have gotten experimental error in that?
When you cleaned out the sugar water.
Yeah, maybe I didn't get it all out, right? The last class I did accidentally rinse it out with the tap water, so immediately, my container was contaminated when I did that. But all right, I think that's everything that you need. I believe that's all we want to go over. So if you have any questions, you do have for the quiz next week, or I'll be handing out the test next week. Come see me after class and we can go over it. All right, have a good one.